Hello, everyone. My name is Bennett Meares. I am a graduate computer science student, and I've been working at CEVAC since spring 2019, or for all 4 semesters. It's my job as CEVAC's data engineer to build and design a system to efficiently create and update hundreds of data sets, a process known as ETL, or extract, transform, load. Whenever I mention CEVAC Python, I'm talking about the CEVAC Python package, which Dr. White had mentioned earlier, which is the fundamental software library I've written that powers the CEVAC ecosystem. Here's several screenshots of some of its features, such as accessing the datasets and applying actions to pipes. And there are many technical features I'd love to demonstrate, but for the sake of brevity, know that I feel the Python package is my most significant contribution to CEVAC. Those in the audience who have heard me speak before may be familiar with pipes, but as a recap, CEVAC uses what we call the pipes paradigm when creating and managing data streams. That is, we primarily partition data first by building and then by metric. This provides 2 key advantages. First, it keeps the data sets relatively small to make analysis and aggregations easier. And second, when updating by building and then metric, we distribute the load among several data sources, so we don't inflict unnecessary stress onto any one data source. So for a pipe to work, it needs a definition in the form of a SQL query. The problem is that every data source has its own schema, such as different column names and different table relations. Rather than writing all of these queries by hand, I solved this problem by developing our interface system to produce these standard SQL definitions. Whenever we bring a new data source into the CEVAC system, we simply register its schema to our meta schema, so to speak, and then we can generate a definition for any of its pipes. In this example, I demonstrate a simple look into how Johnson controls pipes are created. Now, we can still write those SQL definitions by hand, and that's where custom pipes come in. By writing our own queries, we can create any arbitrary aggregation of our datasets. Consider the model to the left. We're given 2 pipes from different data sources. We can derive a 3rd pipe from the 2. We've implemented this model in several instances, such as our utilities pipe, which I've shown to the right. From raw facilities and Schneider Electric meter data, we calculate various useful measurements like the normalized, weighted, and unweighted monthly emissions, carbon emissions, and ranking among buildings and metrics, all the while accounting for rollovers and resets. It's likely the most technical SQL query I've written to date. The heart of the CEVAC system is its caching system. It's the engine that maintains the historical data sets. And there's 2 approaches that we come at when getting pipes data. For the caching system, it synchronizes the historical set, which we call a hist table, with the data source's definition. From there, we can then reduce the last 24 hours and the most recent record for each sensor. However, this is limited by how often the data source itself updates. And because Johnson Control's data source is very large, some of the points update irregularly, meaning it can be as fast as 15 minutes or even as slow as 24 hours. For use cases where we want to see live data on a more regularized schedule with a latency as low as 5 minutes, we directly interact with Metasys to build from the bottom up, meaning we build what is the most recent record for each point, and then we handle storing that historically. What I've shown on the right, we use a protocol called MQTT. It's a popular Internet of Things protocol, and it's one of the ways in which we distribute this live data streams through a publish-subscribe model. We can consume our data through our historical set or by directly hooking into a data stream. To allow developers and users to access our pipes, I've built the CEVAC REST API. Using CEVAC Python, it caches requested datasets to act as a buffer between our SQL backend and our clients. Additionally, the API may be scaled to meet high demand and protect our backend. I've also built functionality into CEVAC Python to sync pipes from the API rather than from the SQL backend so that non-administrators can safely access our data. And the screenshot on the right is an example of some of that live data I had mentioned earlier. So I've demonstrated various iterations of the administrative console in previous presentations, and this is the most functionally complete and stable version of the console. In short, the console is designed to assist administrators like Tim, Dr. White, and Snow in interacting with CEVAC Python. From here, you can create, monitor, and perform actions on our pipes, such as viewing the latest records in historical set or the state of our live data. In summary, the CEVAC system is well equipped to handle any data stream we throw at it. I've spent the last 4 semesters learning so much and meeting so many great people, and I'm tremendously excited to see what CEVAC does next. Thank you for your time.